All right. I hope my voice is audible. Is it? Yeah. So, good evening, everybody. Let us do some coding today as we do every day. All right. So, let's get started with our syllabus and where is the syllabus? Right. All right. So, these are our ADS programs. And, since we cannot do right, since we cannot do these all by themselves now, we will go from the basics. Write mini versions, okay. Before touching a weird tree, understand clean BSD. Okay, insert into normal BSD. Find the height of the tree. Check balance factor, okay. So, not for the B tree, just store key sorted, okay. Binary search inside a node. Simple script operation, okay. Linked list pointers, but no merge yet. Array representation of a binary tree, okay. Insert into heap without percolation. Heapify only downward. Adjacency matrix creation, adjacency explanation, simple data, queue. Okay, it has written prerequisites for everything. So I will copy this order here and we will follow that order itself. Okay, insert into BSD in order traversal and delete, okay. So let's subtract smaller values, right? Subtract larger values. Okay, and also we need to do the dry run of the code. For doing the dry run, I will get this thing as well. Yep. Alright. So first we need to declare the node and we need to create the node. So this should be simple. Node structure, create it and insert it. Create, you need a value and you need to insert at root and you need to have a value for this as well. And you need to do the in-order traversal. This is a recursion and this is obviously recursion as well. And everything in the main function. Alright, sounds simple enough. Let's get into coding. Because I should be getting my spectacles as well. Okay, cannot drag this. Got it. Yep, this is a preprocessor directive. Alright. And this is another preprocessor directive. In struct node it will have int data and it will have left and it will have right. That is basically the node structure. And so since you cannot directly return a node, you are returning a pointer to the node. Hope that is that one. Alright, struct node, new node. We are using the malloc function. Struct node start of malloc size of struct node. So inserting the data as value, initiating the left as null, and initiating the right as null. And return, what are you going to return? You are going to return the new node. This is basically the create function and now you need to insert into it. So it will take a root. Do you need to put a star to the root? Yes. Let's see. And it will also take them data. So if root is equals to null, you are going to return the create function. This is basically the base case. If that's not the case, you are going to insert into it. Okay, I don't want to look into this code. If data is less than root of data, you are going to insert at the left. Right? If that is greater than the root, you are going to the right. If that is not the case as well, you are going to return the root. No duplicate values are allowed. Let's alright. After going into the else block, we will return the root as well. That is basically the void main and data array. Let's say 1, 2, 3, 4, 5, 6, because why not? And we have 6 values here, so the n is 6. We can do the array dynamically as well. And we are doing int I. So I is equal to 0, I less than 6, I plus plus. Root. Okay, before that you need to initialize the root to null. Struct node root is equals to null. Okay, and also you need to write a traversal function, right? So void, let's do something like in order. And what is the parameter it is taking? We need to traverse the root. So if root is equals to null, you are returning nothing. Alright, if that's not the case, you need to traverse the root of left, and then you need to printf, that's a % max slash t, root of data in order root of right. So it is a recursive function which calls itself. That is it. Root. Okay, here you are calling the insert function instead of writing it those many times. So root and data of I. So and then you are calling the in order root. I really assume there are going to be errors in this code, but well, that's how you learn anyways, right? Right? Value. Okay, this is not value. You have taken data here, so that should be data. Okay, it compiled and it is just printing. But that should not be the case. It compiled, but I think there is an error here. Let's see what the error is. It compiled, but I think there is an error in this code. Okay, it's a logical based issue. Okay, it becomes highly skewed. Wow. Wow. Okay, it is just the input. I mean, that is how BST comes, right? Oh, absolutely. Let's do something like this. Right. There is no logical issue. Okay, nice. 6. Okay, the in-order traversal is it just okay. Wait, the in-order traversal of a BST just prints the ascending order. So it printed the ascending order. So why should I be worrying about? If you do something like this, it will do the pre-order traversal. Then you will not get this. See? And if you do something like this, you will get a post-order traversal. This results in a post-order traversal. Nice. So we do it correctly. Okay. So you are inserting at a specific node. This is the base case. If there is no root, you are going to create the root. And If the data is smaller, you will go to the left and insert it over there. And if the data is greater, you will go to the right and insert it there. So my code is working. Okay, where is this one? Did I close ChatGPT? Yeah, I did. So all the program's fine. So the logic is fine. Structured correct and functionally correct. That is great. Right skewed BSD. Only technical issue, okay, but that's nice. Yeah, let's do that. Okay, I don't know, I could. Even I do not know that I can implement this by myself. Is it just okay? Someone else is watching. Hello there. So yeah, leaf node, that is first case, and it has one child, that is second case, and it has two children. Yes, for two children you need to find the in-order successor. Try deleting the front nodes, okay. So I wrote the create function, I wrote the insert function, and we are supposed to find the minimum element. Let's say you're finding the minimum element from the root, you need to traverse to the left and so it is a pointer that is pointing to the root, and let's say it points to the leftmost child, that is the smallest value, and you will return that. Delete node, okay. So first search for that. That's recursive calling. First search and locate the node. And after searching, this is just recursion. This is recursion. So the case for no child is obviously it doesn't have row left and it doesn't have right. So you will just free that and you will return null. Nice. And if it has only one child, this code is looking more structurally correct to me now. So first search it and found it. Or you can just write the search function in the delete node function. I mean, it will. So I got a doubt here. If it entered here, it will enter this recursively. And since the if case got executed, it should return. Okay, wait. We are not returning anything from this to get out of the function. Okay, I got my doubt cleared. So, yep, no child case and one child case. Okay. But you are not making any connections, are you? Temp is equals to root of right, okay. You will free that and return the temp. You will free that and return the temp, okay. Two children. Okay, in the root of right, you will find that. So that's called in order successor basically. And what are you storing? Temp stores in order successor. You will just replace that root of data is equal to temp of data and root of right. So okay, you will delete the successor. Okay, I understood most of it. So you are replacing the root with the in order. So what is it returning? It is returning if you look at the delete node, it is returning a pointer to a node. In this case, it is returning null. That means there is no child to return. In this case, it is returning the right child. Okay. And in this case, it will return the left child. And in this case, it will replace the root with the in order successor. Okay, you are intentionally to delete the root, and to delete the root, you must replace it with in order successor. Since the in order successor is a new root, now you need to delete that old in order successor. So you need to delete that. Apparently, this line of code uh, removes the in order successor because it is a recursive function. Okay. In order, okay. Alright, I have understood most of it, but the recursion takes care of reconnecting it. Okay. So you are deleting the root here is 10. Okay, key is 5. Since since 5 is less than 10, go left. Okay, it will delete 5 comma 5. It has only one child, so what happens now? Now look at what happens in call 1. Okay, it recurses. Okay, You are attaching it. Nice, nice. So what are you doing for the two thing? Like two children guys. Okay. So that is the beauty of recursion. Right. So okay. We did BST creation, we did BST insertion. Now we will be diving into BST insertion. Correct? Is this viewer just me or yeah, yes, there is another viewer. Is it? Yep. Alright, so let's get this started. We need to write the dry flow rate. So what will we do for deletion? For deletion involves three cases. No child case, one child case, and two child case. So return nothing. You will return null for this one, and for one child, you will return the child. And for two children, in order successor and root swap. So you will swap the in order successor and the root, and return the node. Are you returning something in the two child case? Okay, that is good. What if you write the return root here? First, you are supposed to find it. Obviously, this is the base case. If there is no root, you will return the root. Then it will go to insert function and it will create it. So first you will search it. Write everything in the else part. Okay. Since you are not returning anything, Okay, let's ask this doubt as well that I got before for more clarification. Yeah, that is how C works. That's how we want to get 7 and you will okay. Yes, because if the if condition was true, completely skipped. Oh yeah. Oh yeah, yeah. Is it enlightenment? Yeah, it is enlightenment. Recursion return value 6 for you. Writing the logic for one step, let recursion handle the entire structure. Yeah, that really seems the case here. I missed up. I missed a very important concept in programming recursion. So that's why everything felt like magic before, but now things are working. So it will go to left, it will go to right, and if this is not the case, and if this is not the case, that means that is the equal case. If it is not lesser, if it is not greater, that means it got to be equal, right? So then this part will get executed. The no child case, you will free it and return it. The one child case, if left is equals to null, right? Then there see if you say this, both left and right are null, it will get returned. So if this is not the case, that means only left is null. Because if right is null as well, this will get executed. You will store that and the root of right will be the pointer to the root of right will be stored in temp and you will free the temp and will return that. Sorry, you will free the root because you found the root. You are copying the child into temp and you are returning the child. Similarly for the right case. Okay, I think I need to put a water bottle over here. So if there are two children, okay, you need a helper function for that. What is that? An in-order successor. So for an in-order successor, you are finding the smallest element. And in the right, so I will tell you how an in-order successor works because Why not? Let's say we have a tree like this. Alright. 3 and 7 and 13 and 20. This is a valid tree, obviously. So you are, let's say, deleting this. And so if you look at the in-order traversal, it will start from here. There is left. It will go here. There is left and there is no left. It will print the root. It will go to the right and then it will print the root and it will go here. This 15 and 15 has left. Then it will print the 13. So 13 is the in-order successor of 10, right? So 13 is in order successor of 10. We need to retrieve this value. And after that, what will we technically do is we will put a 13 here. We will put a 5 here. We will put the 15 here. This left subtree is going to remain unchanged. And you will get the 20 here. You will eventually delete this 13. So that is how the code works. So you are copying the 13 to the 10. So it will have 13 and it will have 13 here as well. So you need to delete this, and to delete this you will just what will you do? You will recursively call the delete node function at here. If you recursively call the delete node function at here, prompting to delete the value stored in the temp, it will eventually delete this one. That is it. Now everything is coming together to one line. Okay. So this is how you delete. That's why you need to have an in-order successor. Right, and as root and okay, in-order successor and root swap and delete it. And delete the successor. Obviously recursively. Return root at the end because we don't need what will happen if I write the return root here? That is an important question. Yep, this. Both versions behave the same. All deletion cases must end with the return root. Nice. Yep, so now I'm thinking like a programmer. You can write the return node at anywhere, doesn't matter. So 40 minutes. And we are trying to understand the BSD code. Okay, all of this remains the same since we have written it. So in order successor, right? Let's do min element. Obviously, it is supposed to return the min element of the root. So how do you get the min element? If root of that is not is equals to null, alright, so what is happening? So you will get the minimum element. You are supposed to get the minimum element. So, alright. Is it a recursive function as well? Yeah, I mean, why should you write it recursive? Because there is a condition. Why root of left is not equals to null, root is equals to root of left, and it is not returning the element, it is returning the pointer to the minimum element. Right, so once you found that, what you are going to do, you are going to return and change root. That's it. So you got the minimum element, and what will you do now? You will write the delete function. So obviously it will return the pointer to the node as well. And what parameter should we be passing? We need to delete what and we need to delete where. So do we need a root? Yes, we need a root. I think because to write both insert and delete functions, we need to have to start from the root, right? So that is required. Okay. First, what is the base case? If root is null, you are returning the root. I don't care about it. If root is null, then it will return the root, then it will go to the insert function if you are trying to insert something. So this is the case in which you don't care. Okay. You can, these are two disjoint cases, so root of left. Okay. Before deleting, you need to find it, right? If value is less than, if the value you are trying to delete is less than the root of data, then you need to recursively call the function to the left. Okay. And if that is not the case, it might be smaller or it might be greater. Value is greater than root of data. When it's greater, you need to look at the right. Root of right is equals to delete now. Root of right value. You delete. You will search for the right. That is just a recursive call. And after that, what will you do? You found it. If that is not lesser, if it is not greater, that means it is equal. And you found it. So, hooray. You found the node. Alright, what will happen now? Guess I need to drink some water. I will get back. I don't know if the view count is accurate, but it doesn't matter. So you found the node, and after that, what will you do? You will write the three cases. If the root of left is equals to null and root of right is equals to null, there are no childs and you will return nothing. Okay, you are supposed to delete the root, free the root, and return null. So if that's not the case, if root of left is equals to null, that means it has root of right. So you are storing it in the temp, and you are freeing the memory of the root, and you will return temp. And if that's not the case as well, root of right is equals to null, that means there is left child. All right. So this is the zero child case, and this is the one child case. We completed that, and now we are supposed to write the two child case. Okay. So this is the two child case. For two child case, you need to find the minimum element. All right. What is the function again? Min element, right? Yes. You need to find the in-order successor. I have told you why you should be writing the in-order successor here. So you are storing it in the temp. And what are you doing now? So you are swapping the data. Why is the root not working? Yeah, there is a bug here. I told you. For the first time, when you use this, I don't know what's this called, pointing operator, it is not showing that drop down box. For the second time, it is showing. So root of data equals to temp of data. You swap the data, and you are supposed to delete the node recursively. So after swapping, can't you just... Okay, I got it out here. Let us ask it out. And in the two child case, when you swap the root with the in-order successor, can't you just free in-order successor? Can't you just free temp response to the in-order successor? No, this will corrupt the tree. This does not delete the in-order successor node, it only copies its value. Okay, there will be pointers even if you free that, and that pointers will corrupt the node. Okay, and root of right is equals to delete node. Deletes the node or successor node recursively, right? Um, okay. Start deleting 55 from the right subtree. Oh yeah. Okay. Finally, somebody send me a love emoji. All right. So you are finding the min element, and you are storing it in the temp, and you are swapping that the root of data with temp of data. And after swapping, you are supposed to delete that node as successor. You need to start from the right child. What are you supposed to delete? You are supposed to delete the temp of data. And you will return the root. That is great. You have written deletion as well. Under 88 lines of code. Wow. And root is equal to delete one. Let's say let's delete the 14, shall we? And let's do the in order traversal root again. Let's see if things work. Okay, I forgot to write a backslash n here. So after deleting, let's print backslash n should work, if I'm not wrong. Nice, nice. You have successfully implemented a binary search tree without any problems. That is a great news. All right. Hi, bro. Welcome to stream. Yeah, I am from Srinagar, by the way, if you don't know. All right. One step forward to the AVL trees. Guess I'll take a small break. Should I? I have been saying that I will bring the water bottle from a long time, but I'm not actually bringing that. Yeah, I have a small work to do. I will get that done and I will come back to the stream again. So I'll be stopping the stream. So have a great day, everybody. Right, I'll come back in 10 minutes or 15. So bye.